Okay, so it looks like everybody's about here. So let's get started. So today I'm going to lecture a little bit, and then going to go over lab one. We're going to do lab one. I told you yesterday I was going to do 2 lectures today, but I think that's too much talking. So I'm just going to do the rest of yesterday's lecture. And then what I was going to lecture on today, we'll do tomorrow. Okay. So that'll put us a little bit behind already on the syllabus, but that's fine. We've got plenty of slack in there. But before I get started, I prepared for you something called guided notes. What guided notes are is me building out the structure of notes of what I think is important about today. Now, I'm not going to do this very often. I just wanted to show this to you, so if I do it again in the future, you'll know what's going on. So basically, what you do is you can follow along with my lecture, and then as you hear stuff, you just fill this out. Okay? And that's your notes for today's class. Kind of cool, right? That way, this is what I think is important from the material. And that way, you've got it captured nice and succinctly. So, that being said, before, let me show you what you need to do. Don't ask me for edit permission on these Google Docs. You just go to File, make a copy. Okay? And you have your own copy that you can edit and do whatever you want to with. Okay? And if I do these things, they'll typically be in the front of my slide deck on this material slide. I pretty much put all the links that I referenced here. Okay. When we do GitHub stuff, are you guys familiar with GitHub? Source code that I use in class, I'll be posting to GitHub, and then I'll link to the repository here. Okay. So this is the 3rd unit in yesterday's lecture, and this is pretty much very high level how we make computers do what we want them to do. The gist of this topic is that we write instructions in a format that we can read called source code, then that gets transferred and translated into a way that the machine can read. And there's several layers in there. The first layer is going to be the hardware, and then above that's going to be the operating system. And then this object code is stuff that the operating system understands. The operating system will take this and deal with the hardware. There's a lot of CEs in this class. How many are CEs? So y'all are going to be very, very intimate with this process by the time you're done here. Okay? So we write instructions in the form that humans understand. That's called source code. And then that gets translated to instructions the computer understands. That's called object code. So let's look at a very high level picture of a computer architecture. Like I said, this is very, very high level stuff. You're going to get way more details in your CE degree. But in general, there's typically some kind of CPU, and that's central processing unit. We have some volatile RAM, volatile memory. This is RAM. And then we have I/O. And I/O could be anything from keyboard input, touch, video, audio, hard drives are here. And this is the basic argument. The CPU processes instructions, deals with events from the I/O, uses the memory to store data. Very, very simplified. That's how it works. How we send instructions to the CPU. We write something in human readable form. Can you read this? What does it say? What? Yeah. And we can intuit what that's going to do. If A is less than B, what's going to happen? It's going to print X, right? We can understand this. The computer can't, though. Okay? The computer can't. And so what we have is a compiler that takes this and will translate it to instructions that the computer can understand. And that's called object code. Can you read this? Exactly. The computer can't, though. Right? Now, if we were to write in this, it'd be very difficult. It'd be difficult to understand what's going on. It'd be difficult to maintain. It'd be difficult to change. But I'm right here. This is easy, right? Now, of course, this is a very simple 3 lines. When we get the software systems, they get very, very big. But still, this is the idea. Now, One of the issues here is that these compilers, when they write to stuff that computers can understand, these are specific to the computer, right? And so let's say that we had a program that was for a Windows executable. And we wanted to manipulate the UI, manipulate the screen, maybe pull some stuff off a USB device. So we would have to have instructions that were specific to those APIs, and then the compiler would compile it specific to that hardware. But what if we wanted that program to run on a Mac? They might have different USB drivers, right? They may have different instructions on painting the screen. Well, we would have to write a different piece of source code. And we would have to have a different compiler. What if there's a major revision in Leopard, or what's the current Apple operating system? Anybody know? Well, let's say we're going from Windows 7 to Windows 10. Now, Windows, they don't make a lot of big structural changes. Let's assume they did. We wouldn't have to have a different compiler for the two. In that case, we don't. But we have different compilers for 32-bit and 64-bit. Now, let's start this up. We have different compilers for the different architectures, for the different operating systems, for the different platforms, whatever. And then we have to have different source code, too, because they have different APIs, different libraries, different requirements. This gets to be pretty cumbersome. Has anybody developed Android? Anything commercial for Android? Or just toying around? Okay. That sucks if you're trying to do something commercially because the Android ecosystem is so fragmented. There's so many different versions of the libraries out there. It's similar to this, okay? But not exactly. So when Java comes along, it says, okay, we're going to do something differently because this is difficult. So we're going to do something a little differently. We're going to introduce this intermediate step called bytecode. And so what Java says, I'm going to give you a consistent API to do printing, to do GUI, to do USB, to do I/O, to do whatever. And then, regardless of what platform it is, we will translate that on the fly using the virtual machine. So for the developer, you've only got to write code once, and it'll run on anything that has supports a Java virtual machine, or anything that Java virtual machine has been written for. Remember when you go download stuff, you saw the JDK and the JRE. The JRE stands for Java Runtime, and that's the virtual machine. Do you guys know what a virtual machine is? Someone? For those that don't, it's software that acts like hardware, loosely. It's what's called a virtual machine. And so what we have here is Java says, the Java developers say, I'm going to write a virtual machine that works on Windows 10. I'm going to write a virtual machine that runs on Apple, iOS. I'm going to write a virtual machine that runs on all these other different platforms. And so that way, and I'm going to expose a consistent language and API out of that virtual machine. So whenever the developer comes along, he's only going to write one program. And the virtual machine will do the translation to whatever the specific platform needs. And so what this intermediate portable code is called bytecode. If you take a look at it, it will look something like this. Now, this is actually the bytecode from this. What do you see in here? Strings. That's fairly universal. And you'll see strings in here if you go and inspect your stuff. In Java, the source code is a .java file. The bytecode is a .class file. And then this is translated at runtime by the JVM. So when you go to launch it, you have bytecode in your machine, and when you go to run it, as it's executing, this translation occurs. And that's different from compiling, because what compiling does, this translation happens once when you compile it, when you build you an executable. These aren't executables. This intermediate form. Are you familiar with any scripting languages? If you know what scripting language is, that's what's called interpreted. And how it's different from here is that we have the source code, and there's an interpreter that translates on the fly to what the underlying platform can understand. So Java is a kind of blend between a compiled code and interpreted code. It pre-compiles it to this bytecode intermediate format that's portable, and then that gets interpreted. Initially, when this first came out, that's very slow, because there's an extra step of processing, right? Now they've done so many optimizations and programs, it's advanced so much that this is pretty fast. It almost feels like it's native. So any questions about this? Seems kind of neat. Yeah.
You just need to dock class file to integrate your program, right? You don't need to carry a source code around.
Yeah. So what will happen is you have the source code at the command underneath the hood at the command line. You do like Java C, which is Java compiler. You gotta run a tool that'll take this and build this, and then you do Java space and then the class file. That'll run that. So this is all you need. Now they package them into jars. You guys heard of jar files? It stands for Java archive. It's just a zip. You can actually unzip it. Literally, you can say unzip and unzip it. And they just kind of package these class files to certain structures. We include some other resources. But yeah, you just need this. And then the Java runtime. Okay. Yeah, you need the JVM. Later in convenience, I've recorded a desktop demonstration of me compiling something and running it from the command line. In this class, we're going to use IntelliJ, which IntelliJ, when you click run, that's what it's doing. It's dropping to the command line, running Java, and then running Java C, and then running Java. Literally, that's what it's doing. Okay? So you can watch a video of this when you want to. It's only about 4 minutes, so I encourage you to do so. Okay? So now we kind of know how Java works, and we know how Java's portable, and we kind of understand a little bit about why that's important. I'm going to tell you a little bit about how we develop software. This thing called the SDLC, the Software Development Lifecycle. The basic flow is this, that we collect requirements. And when we collect requirements, that's where we go, what do you need? What are you trying to do? What do you want in your software? What do you want in your software? I'm actually asking you.
What do I want in my software?
Yeah.
To work.
He wants it to work. Yeah, right? This is the requirements phase. Why do we have to do this? Sure.
Why do we have to do this?
Yeah.
So we are able to meet the needs of the consumer?
Yeah, absolutely. We can't just sit down and start writing. We can't ever do it for fun, right? But we need to have requirements so we know what we're writing for. So typically, this is done first. Then once we kind of know where we're going, then we do this next step, which is design. At a very, very high level, design is called architecture. Architecture, we need these kind of big components to solve this problem. We like a server. We need a server software that does something. We need a client that does something. We need this pipeline of stuff to do processing. Right? When we refine that and get a little lower level, and we start to say we need these methods, or this library, or this module, or this class, with these methods on it. That's typically what we refer to as design. So here we go, we know where we're going to go, and we say we kind of have some idea of how we're going to get there. And once we do that, we implement. And we actually write the code to do it. Once we've implemented, we start testing to make sure it does what we say it's going to do. If it's doing what it says it's going to do, we write some documentation, and then we release it and maintain it. Now, this is what's referred to as the waterfall process. How many of you have heard that before? So this used to be the way people believed that we did software. And in some organizations, like let's say like maybe Rockwell Collins, where they do avionics, they will follow a process like this. They have a lot of risks that they need to manage. Nowadays, though, we do something more agile because it's hard when we're doing requirements. Really, what we're doing is we're trying to predict the future. Because you say you need this and this and this and this, but until we actually give it to you, and you go, oh, I didn't really need it like that, you know. And there's very, very often in our domain that what someone says they need and actually what they need is disconnected. So what we do now is that we take a more agile approach. We use something, a lot of people use something called Scrum. And they do, deliver this, little bit of this, a little bit of this, a little bit of this, give it to the customer, and then do it again. About 2-week sprints. So it's very, very fast. So we're only committing 2 weeks before we get feedback that says whether it's right or wrong. Right? That's very, very important. Because on a bigger project, let's take, you guys have heard of the failures with healthcare.gov, right? They did, I'm sure they did this big waterfall process that's typically government regulated. So they probably sat around for months and months and months and months and wrote documentation, specifications, requirements. And then when they go to put it out there, they're like, oh, it's not working. But they committed this year's worth of effort before they released anything. That's an investment you can't recover if you make a mistake. But if you're doing, actually when they fixed healthcare.gov, by the way, it's because they went to an agile approach. They started doing the small, quick increments. If I'm giving you a product every 2 weeks, we've only lost 2 weeks if I did it wrong. Or if it's not what you need. So now we do a little bit, and then if you heard of TDD, if you guys heard of like test-driven development, they'll do requirements, and then write tests. The tests will reveal the design, then you write the code. I write the tests first. And this is a really great way to program. Because you know by the test, when you write the test, this is how you're using it. So the test goes, oh yeah, I'm going to use it like this. And if I use it like this, and I give it this value, I want it to give me that value, and until your code does, it's not right. So we can do this, then this, then these, that's TDD. The shorter the increments that we do the cycle in, the more agile we are, the more risk we mitigate. This phase here, this is somewhat controversial. The agile people say that the code itself is self-documenting. The code is the truest artifact about what the system does. It contains the design, and it contains the implementation. And so the agile people say we don't need another set of documents that repeats what we have in our code. Maybe if we're writing something for the government, or if we're flying a plane, we might produce this type of stuff. Agile folks believe code is self-documenting. But in maintenance, believe it or not, statistically, 90% of an application lifetime is spent here. In this part, 90%. And statistically, the later we find the defect, the more expensive it is to do. If we make a mistake in a requirement on a piece of paper, it costs us a few bucks to change. But if that mistake propagates through into the real world, it can cost us thousands of dollars to fix. The earlier in the cycle, the cheaper it is to fix problems. Make sense? All right. So here's what I want you to do. Go here. Take this short quiz. This is not graded. Remember I talked about interrupted forgetting. This is just close your notes, don't do the notes, just to help you remember this content we talked about today. It's just 3 short questions. What? Oh, do you not have the slides? Go to the syllabus, go to the slides. That's in the slides.
Day 1 or day 2?
Day 1. We'll do day 2 on day 3.
Day 1 is just like a course introduction.
This is the third part of that. The watch is the video.
Yeah, I get it.
Yeah, sorry. I was just doing that just a second ago. You're right, it's a little unclear. Let's look at the same URL. I'll put on new liners. Yeah, it's two different URLs. Yeah. Scrum. SCRUM. Yeah. There's a bunch of different processes that people use. Scrum is pretty popular right now. Go to all the way towards the end, get the unit 3, then it's like, thank you. Now, don't be looking at your notes. Don't look at notes to answer the question. Oh, okay. Okay. Sure.
My email's not.
You sure you're in this class? Yeah. Okay. Who else's email is not in the list? Anybody else? Just you? What's your email? I'll take a look. I might have copy and pasted wrong when I built the form. Is anybody still doing it? No? You are? Okay. This is not graded. This is just help you remember the material. Let's just go through these real quick. In general, after we collect and analyze the requirements, we start to design the system. Typically, you might start an architecture, some high-level view. For a long time, my process for this was napkins and circles and boxes. We'll teach you UML, which is actually a modeling language that you can use to do this kind of stuff. The design phase is when we determine the needs and wants of the customers and users. That's false. That's the requirements. That's where we go out and determine what we need to be doing. The interesting thing about this is that each of these things, I kind of went them very, very fast, but they're actually subdisciplines in software engineering. If you're a software engineer, you'll take a class in requirements. You'll take a class in testing. Take a class in process. That's what we'll do as part of this curriculum. If you're CE, I don't know what you guys do. You guys go off in hardware land, and I never see you again after you're freshmen. In Java, the compiler translates the source code that we wrote, and the JVM is what executes it on the host machine. And this is what gives us portability. Because then we only need a JVM per platform. You can have 20 Java apps on there, and they don't need to be compiled for that thing. So this JVM and this portable bytecode is what gives us Java its power. And this one is true. Okay. There's one more thing that I want you to do before you go today. And this is a short formative survey. And what a formative survey is it helps me adjust the course. And I'll ask you this same survey again in the middle of the course, then again at the end of the course. And these are anonymous. So just a little bit about yourself. And now it says that bi-weekly exams, that's actually now every 3-week exams. And then a few other questions. So please do this. This will help me keep the course fresh and interesting. Thanks. How familiar are you with software development? Yeah. How would you rate yourself? Yeah. Okay, so let's go over, let me give you a couple important links first. MSOE.us/Taylor/SE1011. The way we do courses at MSOE, so you know how we have small class sizes. How we get to small class sizes is that we have a bunch of instructors teaching. But in order to keep consistency, we dedicate one person to be the course coordinator, kind of like the owner of the class. He kind of designs it and manages it, kind of keeps us all within the same river of instruction. Now, of course, we all take some latitudes in there, but generally that keeps things consistent, which is very, very important in our degree programs because you guys all march on together, cohort to cohort, and that you need the same skills as your peers when you move on to the next class. So he's the course coordinator for the entire freshman sequence. This is his website, which has a lot of useful material. You can see the outcomes. This is where I get my outcomes from. You can see his schedule. This is generally where I get my schedule from, although we will veer. Okay. He'll also post videos of his classes. I'll be posting videos of this class recorded. He provides homework to his sections. I don't assign homework, but if you want to do some practice problems, you can go track to see what he's assigning. This is what he thinks important. And what he thinks important is very relevant because we follow the same set of objectives. He also has a set of tutorials that you can go back in for review. This primitives versus refs, we'll actually be doing that on Monday. Okay? This will actually be a topic we do Monday. He will have a link to his code repository for the code that he submits for his classes. I will use GitHub, and that's where I'll put the code for this class. Okay? But it might be interesting to go see what he's doing if you're trying to prepare for an exam. And then for his exam archive, if you go up a directory, to MSOE.us/Taylor, you can see here where he has exams. He has full sets of 1011 exams. Okay. Now, since you saw how specific our objectives are, and so these will track fairly well. Okay. Now, the scheduling might be off a little bit, so what's on his exam one might be a little different than what's going to be on our exam one, but they're going to be fairly consistent. So you can use it here for a body of exams. So now let's talk about lab one. So before class, I wanted you to download the JDK. This allows you, this is the software, this is the Java development kit. This allows you to build Java programs, including the Java compiler, the Java runtime. And I wanted you to install IntelliJ. How many of you completed this step? Everybody? Okay. No, okay, so everybody has. And then basically what we're doing is we're just going to copy and paste a program into IntelliJ and run it. The purpose of this is just to make sure that your laptop is capable of compiling and running Java programs for future labs. Not to teach you anything about Java programming. It's just to make sure that your stuff's configured and you know how to run one. Create a project and run one. So let me show you how to do this. So when you launch IntelliJ, you actually might get a little wizard. This is like new project or whatever. That's fine. Say new, you go to project. You skip this stuff. Now up here, if it's the first time you've done this, this will be blank. You'll need to come here and select new. JDK, and then go find where you installed the JDK that you downloaded. Okay, and you need to point it to the parent directory, not the bin. Now I've already done it, so I'm not going to point it to IntelliJ's. That's just telling IntelliJ which JDK to use. So when it calls Java C to compile, it'll call that Java C. This makes it easier because it gives you some structure. If you just say command line app, we'll talk more about this later. So if you don't know what that is, that's fine. For this lab, for the project name, you want to call it Lab 1. Your base package, you want to call it Taylor, and I'll explain that in a minute. Then if you click Finish, oh yeah. So I've already done this. It'll get you to this point right here. Okay, so what we need to do is, if we look at our lab, this class name is Lab 1, okay? In Java, it's a requirement that your class must match your file name. So if we just copied and pasted right now, the class name would be different than the file name. So what we need to do is we need to come in here, we go in here, and we say refactor, rename file, and we're going to call it Lab 1. See, now the editor's barking at me because the class and the file name is different. Copy. Control S will save. And then we can go here and we can say, right click, run. See this busy stuff down here? Compile it. And here we go. You can do allow. And now the program will work for you. That's the extent of the lab. You get it to this point, come show me, and then you are free to leave. Any questions? Is it help or questions? Okay, okay.